Here we have the infinite series of natural log of n divided by n squared plus 1. And we want to use the limit comparison test to show that this series right here converges. And so again, to use the limit comparison test, first we call this sequence right here a sub n, and then we need to come up with a series b sub n. And if we want to show that this series converges, then we must show that the limit of a sub n dividing by b sub n is equal to some finite number greater than 0. And then we also need to show that b sub n converges, and then we can say that this series right here converges. So first, we'll let a sub n be the sequence ln of n dividing by n squared plus 1. And then we'll let b sub n be something similar. So we're going to let b sub n be the sequence without a 1. Now we need to show that the limit of the ratio a sub n dividing by b sub n is equal to a positive number. So this will be ln of n squared divided by 2, and this will be ln of n dividing by n squared. And then we can simplify this as follows. Dividing by ln over n squared is the same thing as multiplying the reciprocal. And right here we can see that ln and ln will cancel out. And what's left is n squared dividing by n squared plus 1. And then now we can divide the top and the bottom by n squared. This will be 1, and then n squared dividing by n squared is 1, and then plus 1 dividing by n squared. And this will be 1, and this will be 0, because 1 dividing by infinity is 0, so we get 1. So this is equal to 1. And therefore we have shown that the limit of a sub n dividing by b sub n is equal to 1. And so we have shown that this is equal to 1, which is greater than 0. And so we want to show that this limit of the series a sub n right here converges. And so the next thing we need to show is that the series b sub n converges. So now we need to show that the series L of n dividing by n squared converges. And to show this, we can use the integral test to show that this series right here converges. So before we do that, notice that if we have limit of b as b approaches infinity of ln of b dividing by b, if we let b approaches infinity, then this will ln of b approaches infinity, and then b approaches infinity, so we have infinity over infinity. So we can use L'Hopital's rule, and so we can take the derivative of the top, which is 1 over b, and the derivative of the bottom, which is 1. And then we get 1 dividing by infinity, which is 0. So the limit of this quantity right here is 0. Now we can use the integral test, and then we need to show that the integral of ln of x dividing by x squared is equal to some real finite number. And so this is 1 to infinity, so we're writing it with limit, and then we let b approach infinity, and then we'll have the integral from 1 to b. The antiderivative of ln of x divided by x squared, and we look on the table of integrals, and then we will see that it's negative 1 divided by x minus ln of x divided by x. So the antiderivative of the of ln of x divided by x squared from the table of integrals is negative 1 over x minus ln of x divided by x. And then we need to evaluate from 1 to b. So first, in the place of x, we put b, so we have b, ln of b dividing by b. And the next, minus, in the place of x, we put 1, so we have 1 and 1 here. As b approaches infinity, 1 over b will be 0. As b approaches infinity, we have shown up here that ln of b dividing by b is 0. This is minus negative 1, we get 1. ln of 1 is 0. So we get 1. And so the this integral right here converges to 1. And so by integral test, the corresponding series, this series right here, converges also. And one more time, the integral converges to 1. And then we know that the corresponding series converges, but it does not converge to 1. It converges to something else, to some other real number. And so now back to our problem. Originally, we want to show that the series a sub n, which is ln divided by n squared plus 1, converges. And so first we have to show that the limit of a sub n dividing by b sub n is equal to some positive number. And we have shown that it's equal to 1. And then next, we need to show that the series b sub n, which is the series ln dividing by n squared, converges. And then we have shown that using the integral test, that the series L sub n dividing by n squared converges. And so first thing, ln of limit of a sub n over b sub n equal to a positive number, and then the series b sub n converges. Then we can say that the series a sub n converges. And so by limit comparison test, the series a sub n converges.